All right, so now we're going to revisit something that we saw back in Gen Chem 1, which has to do with the pH, and we'll take a look at the pOH as well. So we saw previously that we can identify a solution as being a neutral solution, acidic solution, or basic solution by comparing hydroxide to hydronium concentrations. There's a much quicker way to do that, to say whether something is acidic, basic, or neutral, and that is by using the pH scale. So the acidity, or we can say the basicity of a solution, depends on the concentration of the hydronium, the H3O plus. And we define the pH of a solution as a negative logarithm of the H3O plus concentration, right? So pH, we define this as a negative log of the concentration of the H plus. And again, right, H plus is the same as the H3O plus, but it can also be written as negative log of H3O plus concentration. Where the concentration again is in units of molarity, moles per liter. This is very important when we look at pHs because this is a logarithmic scale or logarithmic calculation that we're doing. So something that has a pH of 1 versus something that has a pH of 2, right? Doesn't mean that there's just a 1 pH difference between them. There's, in terms of the concentration, it's 10 times more concentrated in terms of the H plus. Right. Similarly, if something has a pH of 1 versus a pH of 3, well, the pH of 1 is 100 times or 10 to the 2 times more acidic than the pH of 3. So you want to keep that in mind when you interpret your pH values. We can, if we wanted to, we can rearrange with equations. So if we're given the H plus concentration, we can obviously just plug it in to find the pH. What about if you're given the pH? If we measure the pH, right, we can actually solve for the H plus concentration by taking 10 and raise it to the power of the negative pH. Right, that's how logs work. And again, pH is just a number, it's a dimensionless quality. Right, and as a quick reminder, the pH scale goes from 0 all the way to 14. 14 here. pH of exactly 7.00 is considered neutral. Anything more than 7 is considered basic or alkaline. Anything less than 7 is considered acidic. So again, this is something we saw previously. That's how we interpret the pH values, and this is how we calculate the pH values as well. Now, the pOH is something very similar to the pH scale. It's analogous to the pH scale, but it's slightly different. So we define the pOH also as the negative log, but the negative log of the hydroxide ion rather than the hydronium ion. Okay, so if we have hydroxide, we can calculate the pOH. How does that help us solve for the pH? Well, the relationship between pOH and pH is actually very, very simple, and it all stems from that Kw expression. Right? So we can derive that. So we call the the H3O plus times the OH minus concentration was equal to 1.0 times 10 to the negative 14, right? That was the ion product constant for water. If we take the negative logs of both sides of this equation, okay, so we have the negative log of this whole thing here on the left. So H3O plus times OH minus, and that's equal to the negative log of 1.0 times 10 to the 1.0 times 10 to the negative 14. Okay, if you take the negative log of this, you end up with 14. And then if we evaluate the left side of this equation, right, the way that logs work, if we expand this out, this would become the negative log of H3O plus. plus the log of OH minus. Which then becomes a negative log of H3O plus. Minus the negative log of OH minus. And this is still equal to 14, 0. And this is the same as saying the negative log of H3O plus the negative log of OH minus. That's still equal to 14.00. Well, guess what? Negative log of H3O plus, that is what pH is. And then plus negative log of OH minus is pOH. And that's equal to 14.00. Right, so we've actually just derived this equation here. A lot of times we just tell you what that equation is, and it's a very simple equation. But all we've done is taken this ion product constant expression and converted it to a form that is a little bit more user-friendly. All right. So either way, and there's lots of ways that you can do these types of problems when you have them. To solve for pH or to solve for pOH, it doesn't really matter which way you do it. Some ways are longer or shorter than others. To find pH or pOH, if you have hydronium or you have hydroxide concentrations, it all just depends on your, on the time that you have to spend doing the calculation, or depends on what you're more familiar with. So, whether you want to use the ion product to solve for one versus the other, whether you want to use the pH and pOH relationship, either way, with these types of problems, you end up with the same answers. So down here on the left side, we have again our OH minus concentrations, how they correlate to the pOHs, and I'll just put here as a reference the pH values. Okay, so if the pH is 1, the pOH is 1, that means that the pH is going to be 13. Right, so you add these two, you should get 14. Then over here it'll be 11. This will be 9. These are all their zeros. Here it would be 7.00. That's neutral. Here it would be 5.00. Here it would be 3.00, and then it would be 1. Right, so when we talked about the pH scale before, right, we said the pH of 7 is neutral. Anything more than 7 is basic. Anything less than 7 is acidic. Well, the opposite or the reverse would be true when you look at your pOHs, right? Because it's just the subtraction from 14 to get the pOH values.